When electrical problems occur, we are called on to fix them fast. However, trying to work too quickly can lead to mistakes. Today's power systems can deliver a deadly blow to anyone who fails to take the right safety precautions. Your safety is extremely important to us. And for more than 50 years, you've trusted Fluke to provide you with test instruments that meet or beat every safety standard. That's a trust we take very seriously. That's why we've put together this program, to help you work safely. Working safely while making electrical measurements is not magic. Safety results from a simple, winning combination: careful planning and safe work practices, combined with using the right tools. We urge you to pay close attention to this program. What you learn could save your life. When you make electrical measurements, safety should always be your first consideration. If you plan your work carefully, follow safe measurement procedures, and use the right equipment, you can cut your chances of an accident to nearly zero. Your first step is planning. Before you open a cabinet, look over your work environment. Where will you place your meter and other equipment? Be sure to identify a clear escape route you can use in case of emergency. Do you have enough clearance to gain access to the equipment in question and to work comfortably? Are environmental hazards present, such as tree branches or water? Do you have enough light and ventilation? Make sure you have a qualified helper on hand who also understands electrical safety. It's never good practice to work alone on high-energy circuits. Finally, make sure someone else knows where you're working. Another key part of planning is choosing your safety equipment and tools. Make sure you have the required personal protective equipment on hand: eye and hearing protection, gloves, clothing, and insulating mats. And be sure to inspect your equipment to make sure it's in good condition. Check your tools for proper insulation, and make sure your meters and testers are rated and tested for the level of hazard that exists where you are working. Many testers look similar. Make sure you know what yours is designed to do. Next, inspect your test equipment and test leads to make sure everything is working properly. At the end of this video, we'll show you how to test your meter and test leads. Whenever possible, work on de-energized circuits, and always follow proper lockout-tagout procedures. When taking single-phase measurements, always connect the grounded lead first, the hot lead second. After taking your reading, disconnect the hot lead first, the grounded lead second. Use the three-step test method. First, test a circuit you know is live. Next, measure the target circuit. But before you conclude that circuit 2 is dead, retest the known live circuit. This way, you know your meter is working. Try to follow the old electrician's advice. Keep one hand in your pocket. But use common sense. Sometimes you need both hands to make a good measurement. The safest place to measure is where the lowest energy is available. For example, if you're measuring voltage on a breaker panel, identify the lowest rated breaker and make your measurement there. This way, you have more protection between yourself and the potential hazard. Following these steps will help you work safely. But sometimes, even these steps can't prevent trouble. Switching of inductive loads, lightning strikes, and transmission system switching can generate huge voltage spikes. These voltage spikes, or transients, may last only as long as 100 microseconds, but they can be extremely dangerous. In modern power systems, transients are present all the time. some small and some large. But where do transients come from? When an inductive load, such as a motor or transformer, is switched off, it can generate a voltage spike. Sometimes voltage spikes are useful. Your car's ignition system depends on spikes generated by the coil to produce a spark. But when we're measuring power systems, transients and sparks are definitely not good. And here's why. In your car ignition, the power source is weak and the spark disappears as soon as the voltage does. But in a power system, the system voltage does not disappear. And because the circuit is a high-energy source, it can supply current to the spark until the surrounding air breaks down into conductive plasma, causing a major fault. When transients ride on top of the system voltages that supply industrial loads, they can reach thousands of volts, and the consequences can be devastating, particularly for anyone taking measurements on electrical equipment. Under these circumstances, proper procedures alone are not enough. You need to reduce risks by using the right meters and test equipment, tools rated for the environment where you are working, and tested to meet the appropriate safety standards. To provide better protection for electrical workers, new standards have been developed for test equipment used in environments of 1,000 volts or less, including 400-volt and 690-volt three-phase circuits. In the 4-category rating system, the closer you are to the power source, the higher the category, and the greater the danger. Transients in categories, or CATs, 3 and 4 can be extremely dangerous. The available fault current in these high-energy circuits can reach as much as 100,000 amps. Cat 4 refers to power lines at the utility connection, but it also includes exterior overhead and underground cable runs, since both may be affected by lightning. Cat 3 covers distribution-level wiring. This includes 400 or 690-volt circuits, such as three-phase bus and feeder circuits, motor control centers, load centers, and distribution panels. Permanently installed loads are also Cat 3. Cat 3 also includes large loads that can generate their own transients and are now more common than many people realize. The trend to using higher voltage levels in modern buildings has changed the picture and increased the potential hazards. Most electricians work on equipment in a Cat 3 or Cat 4 environment. Many times, people may be working in a Cat 4 environment without even knowing it, and that can lead to real danger. Lower category installations usually have greater impedance, which dampens transients and helps limit the fault current that can feed an arc. Cat 2 covers the receptacle circuit level and 230-volt plug-in loads. And Cat 1 refers to protected electronic circuits. Some installations include multiple categories. This motor drive panel is Cat 3 on the 400-volt power side, and Cat 1 on the control side. Here, you should use the higher-rated Cat 3 meter. In general, where greater fault currents are available and voltage transients increase, measurement becomes more hazardous. This means a higher Cat rating. If you're working in a Cat 3 or Cat 4 environment, you should be using test equipment rated 600 or 1000-volt Cat 3 or 600-volt Cat 4. Let's take a closer look at why transients are so dangerous. Here, a service technician is making a phase-to-phase voltage measurement on a 400-volt motor supply circuit. This is a Cat 3 environment. A major voltage transient caused by load switching or a nearby lightning strike was large enough to cause an arc to strike inside the meter. Short circuit currents as high as thousands of amps can flow for several microseconds. At these current levels, the tips of test leads superheat and the probe tips start to burn away, drawing an arc from the contact point to the probe tip. the technician sees a bright blue arc flash and at the same time is startled by the bang of the arc exploding inside the meter. The arcs follow the vaporized test probes. If these two arcs join through close proximity of the test probes, one large arc is formed, providing a low-impedance path directly from one electrical phase to another. This will cause either a phase-to-phase or phase-to-earth fault. The result is an arc blast, which can lead to a plasma fireball fueled by the energy in the system. When this occurs, temperatures can reach about 6,000 degrees Celsius. Industry sources estimate that in the U.S., 5 to 10 arc flash accidents occur each day. The U.S. Bureau of Labor reports that in one recent year, 1,000 electrical workers suffered shocks and burns, some fatal. It is estimated that 50% of these injuries are related to arc flash. This percentage could be dramatically reduced if technicians utilized the combination of careful planning, correct safe work practices, and use the right tools. Here is an actual arc flash. These fuses were designed to interrupt 10,000 amps of fault current, but are intentionally used on a 50,000 amp circuit. A dead short was created on the load side of the fuses. My name is Ed Manthei, and I have been a professional electrician for over 35 years in Eastern Washington, doing primarily commercial and industrial electrical work. About 2.5 years ago, I had a personal experience with arc flash. I was removing a high-line breaker out of the panel board, and apparently there was an unfused conductor coming off from this main panel. When I moved the conductor, I heard a buzz, and then after that, a major explosion. I was able to get my eyes closed, I think, and my head back a little bit. It blew me back on the floor. Next thing I remember is I was standing in the corner and I couldn't see. My shirt and stuff was on fire, which I didn't realize at the time. I yelled for help, and a fellow electrician came back into the room, took me outside, and put me out with a fire extinguisher. I was in the hospital for approximately 3 weeks the first time. Then I went home, and then in another week and a half, all the skin that had healed on my hands and on the back of my hands and arms started to blister. So I went back in for another 3 days. Then I went home for approximately 2.5 months to see if this blistering would quit. But unfortunately, mine didn't. So then I had to go back in to have 5 hours of surgery, taking all this skin off, and then another 5 hours of surgery to take skin off my legs and put it on my hands and arms. And then after I recovered from that, the following spring, I had to have this finger removed. Then 6 months later, I had to have the end of this finger removed. Me, personally, I have always been accused of being too safe, overly cautious. It's hard to prepare for something you can't see. Make sure that you use the proper safety precautions. I guess the bottom line is that you can't be too careful. Transients aren't the only source of arc flash hazard. One of the most common misuses of multimeters can cause a similar chain of events. If the user leaves the leads in the amp's inputs and then accidentally connects the meter to a voltage source, he has just created a short through the meter. That's why the amp's terminals must be protected by fuses. These fuses may be the only protection against a potential disaster. If the meter is fused correctly, the result is a damaged fuse, which is a small price to pay. Never use the wrong fuse. Only use high-energy fuses specified by the manufacturer. The fluke meter system, which includes the meter's internal circuitry and fuses, and the test probes, work together to properly interrupt fault currents that exceed 10,000 amps. Accessories can also contribute to danger. Test leads can become frayed. If the probe tip is connected and a damaged or underrated test lead comes in contact with another conductor, a fault may result. The same thing can happen if an unshrouded test lead comes out of the meter and touches a conductor. Always inspect your meter and test probes before using them. Please refer to the guidelines provided at the end of this video on what to look for. Remember, test probes are designed for a variety of test environments. What is appropriate for a Cat 1 environment may not be appropriate for a 400 or 690 volt circuit. In a high-energy setting, make sure your test probes have little exposed metal. This will help avoid creating a short if your hand slips off the probes. Meters and other electrical test tools should be independently evaluated to make sure they can survive high-voltage transients. A special test machine is used to generate the overvoltage transient and fault current as defined by international standards. This meter is marked 1000 volts Cat 3 on the front of the case and has been certified by an independent testing laboratory. A 1000-volt Category 3 tester is required to survive a minimum of 10 transients of both positive and negative 8000 volts without creating a hazard. Fluke goes a step further in designing and building our test tools. We build our meters with safety in mind. In addition, we build them to survive. In this test, we have programmed our test machine to increase the voltage in steps until the meter fails. 6000 volts, 9000 volts, 12,000 volts, 15,000 volts, 17,000 volts. This meter finally failed at about 17 kilovolts, which easily exceeded the minimum of 8 kilovolts. Some manufacturers state that their products are designed to meet or conform to standards. But not every meter or tester that makes that claim will pass the test. Here's what happened when a meter marked 1000 volts Cat 3 was actually tested. It should withstand a minimum of 20 transients of 8 kilovolts. But this meter failed twice before reaching the 8 kilovolt minimum level. On a real power circuit, these results could have been disastrous. How could this meter fail? The standards bodies only create the standards. They do not enforce them. A meter that claims to be designed to a standard may have never been tested. That's why it's essential that your tester is certified by 2 or more independent testing laboratories, such as UL in the United States and VDE and TUV in Europe. This is the only way you can be sure your testers have passed the most rigorous tests and meet every applicable standard. Here's what can happen when a meter marked Cat 2 is used in a Cat 3 environment. In a real Cat 3 or Cat 4 environment, the arc would have been fueled by thousands of amps. The resulting arc flash could cause serious damage. In addition to transient protection, a meter should be able to withstand accidental overloads associated with the various functions of the meter. This meter is marked 600-volt Cat 2. Watch what happened when it was connected to a live circuit while set to the ohms range. And if you measure voltage using the amp's input jacks. The fuse would not protect the meter or user. Just imagine if this meter was in your hand and used on a real Cat 3 circuit. Even the most careful of us will make mistakes. That's why your meter should offer a margin of protection. This principle is so important that it has been written into current safety standards. The standards require that test equipment must handle the full meter voltage rating in the ohms and continuity functions without becoming a hazard. To meet the demands of today's high-energy, high-hazard workplace, Quality manufacturers have re-engineered their test instruments to make them more reliable and far safer. Safety is the result of a winning combination. Careful planning and the correct safe work practices combined with the right tools. Use a meter that both meets today's standards and is rated for the measurement category and voltage level where you are working. If you use test equipment on or near 400 or 690 volt circuits, you should use 600 or 1000 volt Cat 3 or 600 volt Cat 4 meters and testers. How does your test equipment measure up? Here are tips for inspecting your own equipment. Look for the Cat 3 or Cat 4 rating on the front and a double insulated symbol on the back. Look for approval symbols from 2 or more independent testing agencies, such as UL, VDE, or TUV. Check the meter fuses for the correct amperage and voltage. Fuse voltage must equal or exceed the meter's voltage rating. Check the condition of your meter. Watch for a broken case, a faded display, or other problems. Check your manual to see if the ohms and continuity circuit is protected to the same level as volts. If not listed, ask for written confirmation from the manufacturer. The relevant standards are covered in IEC 61010. Examine your test leads for finger guards, cat ratings, and double insulation, and look for damages. Check the length of exposed metal. You can use your meter to check your test leads. Turn to the ohms function and short the leads. The meter should read close to 0. Also move the leads and look for an intermittent open circuit, which could signal an internal break. Test the fuses by turning to the ohms function and inserting your red test lead into the amps socket. The meter should read near 0. A blown fuse would read as an open circuit. Then insert the test lead in the milliamps socket. The meter should read close to 10,000. Finally, if you've had a blown fuse or mishap with your tester, make sure you get it checked out and calibrated before using it in a high-energy environment. If your test instrument passes these tests, congratulations! You are successfully managing some of the risks inherent in measuring electrical equipment. On behalf of everyone at Fluke, thank you for watching. We hope you share our commitment to safety. While you can't totally eliminate the dangers of working with electricity, with the right attitude and the right actions, you can significantly reduce them. Remember and use the 3 key steps in that winning safety combination: careful planning, safe work practices, and using the right tools. What you have seen is only an introduction to the topic of workplace safety. We urge you to keep learning and put your safety knowledge to work. After all, the one who benefits most from safety is you. Thank you. And from all of us at Fluke, work smart, work safely.